Hey guys, so today we're going to talk about identities. Our objectives, first we need to recognize what an identity is. It's just a special type of an equation. We're going to state the reciprocal and Pythagorean identities. I'm going to give those to you. And then we're going to use those identities plus our trig definitions to prove trigonometric identities. So that's what we're going to do today. All right, so my first thing I want to do is I want to ask the question, what is the difference between x plus 3 equals 4 and x plus 3x equals 4x? Well, x plus 3 equals 4, x has to be 1. There's no other thing it could be. Whereas on the other side, x plus 3x equals 4x is the same as saying 4x equals 4x, which means that x can be anything that you want it to do. So when you have an equation where the truth, if it's true or false, a true statement or a false statement, if it's conditional on what the variable is, that is called a conditional equation. An equation that is not an identity, okay? Now, an identity is an equation that is true for all values of the domain of the variable, okay? That means it works for any x that you plug in, okay? So let's look at our basic trig functions. These are basic definitions. So first we have sine theta equals y over r. Then we have cosine theta, which is x over r, and tangent theta, which is y over x. So these are all basic definitions that we learned during week 1. Okay, we also have the reciprocal functions. So that was cosecant theta, which was r over y. We also have secant theta, which was r over x. And then we have cotangent theta, which was x over r. So remember, those are the reciprocals. Cosecant was the reciprocal of sine. Cosine was the reciprocal, secant is the reciprocal of cosine, and then cotangent was the reciprocal of tangent. All right, so now that we've got our basic definitions, let's look at what else we can do. Think about this. We are claiming that that secant is the reciprocal of cosine. And really, the reciprocal of cosine means 1 over cosine. So when we say that secant is the reciprocal of cosine, we are claiming that secant is equal to 1 over cosine. And that gives us r over x. How did we get that? How did we get from 1 over cosine to r over x? Because remember, the definition for secant theta is r over x. So how did we get from 1 over cosine to r over x? Well, let's look at it. How did that happen? So first, what we're going to do is we are going to say, well, 1 over cosine, I'm going to substitute cosine for the definition of cosine, which is x over r. So I get 1 over x over r, which is division, right? That's 1 divided by x over r. Okay, so I'm going to go ahead and treat that as I'm dividing fractions, and I get 1 over 1 times r over x. Remember, you keep, change, flip, or multiply by the reciprocal, and I get r over x. Oh, well, r over x, that's the definition of secant. So we went all the way from 1 over cosine, the reciprocal of cosine, all the way to secant just using the definitions, All right, so final statement, therefore, secant theta is equal to 1 over cosine theta. It's important to know that this is, once you prove it, you can use the property of equality, the reflexive property, which says that 1 over cosine is equal to secant. So you can flip them back and forth. Okay, so let's talk about the Pythagorean identities. Okay, so these are coming from the Pythagorean Theorem. All right, so these are the Pythagorean identities that you need to know. We have cosine squared theta plus sine squared theta equals 1. We have tangent squared theta plus 1 equals secant squared theta. We have 1 plus cotangent theta equals cosecant squared theta. So you're like, whoa, where did all that come from? Well, remember that the Pythagorean theorem, when we're relating it to the triangle, formed on the coordinate plane with those trig values. Remember, it's x squared plus y squared equals r squared, where r was the radius, right? The radius formed on that triangle. Okay, so, or the hypotenuse on that triangle. So from there, we're like, well, how did we, let's just look at cosine squared theta plus sine squared theta equals 1. How did that happen? Well, let's look at, we're going to start with the Pythagorean theorem, x squared plus y squared equals r squared. And I'm just going to divide everything by r squared, okay? And when I do that, I get x squared over r squared, which is x over r squared, okay? I'm sorry, these are arrows here. Okay, and then I have y squared over r squared, which is the same as saying y over r squared. And then I have r squared over r squared, which is just equal to 1, okay? Well, I know that x over r is cosine, so I get cosine squared theta. And I know that y over r is sine, so that is sine squared theta, and then equals 1, okay? Well, that's the identity that we wanted to prove. Remember, that was that identity that we were trying to prove. We were trying to prove cosine squared theta plus sine squared theta equals 1, okay? And now that we have proven this identity, we can use it in other places and help us solve even more identities. So it's really fun. So steps on proving identities, or just ways to help you figure out what to do. Okay, so step 1, choose one side of the statement. Okay, you're going to get an equality. Choose one side of that equality that you are going to prove, okay? You will usually want to select the more complicated side to work on. I know that goes against the grain, against what you want to do, but if you choose the more complicated side, you'll be able to manipulate it and simplify it to what you want, okay? Step 2, you're going to use basic definitions that we know, so like trig definitions. You're going to use algebra, okay, so solving for things, and then you're going to also use previously proven identities. So anything that we've already discussed, you can use. So the reciprocal identities, the Pythagorean identities, you can use all those. You're going to use all that to simplify the chosen expression so it matches the other side. Okay, so you're going to simplify, and then you're going to get what's over on the other side. Okay? I want to take a moment and tell you it's important to choose one side, because if you are working on both sides, it is technically incorrect, because that means that you're assuming that the equality is already true, and so you can work on both sides, and the equality hasn't been proven until the end, so you can only work on one side until it's proven. Okay, so step 3, and this is what I call troubleshooting number 3. If you're unable to simplify one side to look like the other side, work on each side separately and see if you can determine the relationship. Now, when I say that, I mean like off to the side, scratch work, because you can't, for your final answer, show working on both sides, because, again, that's illegal. You just want to identify even how to begin, like how to start. So what's the relationship, okay? So again, you cannot use the properties of equality yet, because you haven't proven it yet. You have not proved it. All right, so you can only work on one side, Okay, so troubleshoot number 4. If you find an identity so difficult, what you want to do is you're going to change each member back to its original ratio definition. So I'm talking about y over r, x over r, y over x, those definitions. Go back to the basics and then simplify and see what happens, okay? So, troubleshooting number 5. If you still cannot prove the identity, try some number values in the equation. Plug some numbers in, see if it works. And what you want to do is you want to see if you can find a counterexample to show that it's false, that it's not an identity, okay? And if you can't, then that means that you need to keep working back to step 4 because somewhere there's an answer. All right, so those are the steps, troubleshooting. So now what I want us to look at is I want us to do an example, okay? I have proved sine over cosine equals tangent. So step 1, choose a side. I'm going to work on sine over cosine because that's the more complicated sign, right? Well, I'm going to go back to my definitions, and I'm going to let sine be y over r, and I'm going to let cosine be x over r, right? And notice that my tangent theta didn't change, and that's because, remember, you're only working on one side. The other side should not change at all. So y over r over x over r, that's division, right? So it's y over r divided by x over r. Again, nothing changes on the other side. Shouldn't, okay? Now, I'm dividing fractions, which means I multiply by the reciprocal. I keep, change, flip. Keep, change, flip. I kept, I changed, I flipped, right? And then things start reducing. Good things happening. My r crosses out, leaving me y over x equals tangent. Well, I know that the basic definition of tangent is y over x. So therefore, remember these three little dots mean therefore, sine over cosine is equal to tangent. And because I have proven it, I can now use the equality property and say, well, this is reflexive. If sine over cosine is tangent, then tangent is equal to sine over cosine. And that's super helpful to do that because now anytime you see tangent, instead of writing tangent, you can write sine over cosine. All right. So let's do another example. Let's say we want to prove sine theta times secant theta equals tangent theta. Well, I'm going to work on the more complicated side, which is sine times cosine. All right, and I'm going to let secant theta, I'm going to use my reciprocal identities, and I say, well, secant is the same as 1 over cosine. Remember, we proved that. We proved that, so we can use it. Secant is the same as 1 over cosine. And I just put equals because I know that my tangent theta is just going to keep going down, right? Because it's never going to change on that side. Well, sine times 1 over cosine becomes sine over cosine. And remember, the tangent comes down. So now I have sine over cosine equals tangent. Well, remember, we proved that sine over cosine is tangent. So therefore, sine theta times secant theta equals tangent theta. Okay, one more example. This one looks crazy, okay, but trust me, it all makes sense. We have secant to the 4th theta plus secant squared theta, minus secant squared theta equals 1 over cotangent to the 4th theta plus 1 over cotangent squared theta, okay? Oh my goodness, I know, right? So choose the most complicated side. I'm going to say it's this side. This side is the most complicated, okay? So that's what I'm going to work with. So I know that cotangent is the reciprocal of tangent, and so if cotangent is the bottom, that means I'm actually dealing with tangent to the 4th theta. Tangent to the 4th theta, okay? And then the same over here, I have tangent squared theta. So I'm going to factor out a tangent squared. I'm going to factor out a tangent squared, which leaves me tangent squared theta plus 1. I just factored it out, okay? Now, tangent squared theta is the same as saying secant squared theta minus 1. That was one of those Pythagorean identities that we saw, okay? And then tangent squared theta plus 1 is secant squared theta. Again, that was one of the Pythagorean identities that we saw, okay? Now I'm going to distribute the secant squared theta, and I get secant to the 4th theta minus secant squared theta, which is what I was trying to get to from the beginning. So therefore, they are equal. All right, that was my last example, and thank y'all for watching. I will see you in class.